有没？啊？甘蔗味。几次啊？6次。哪里？啊，对，随便。其实我也有想着我要不要空。我就比较方便哦。诶，罗号有刚才看到罗号好像。哦，我这路来，没有跟你们来。我去哪里？哦，哦，OK OK。啊，我都很快。OK。哦，这样，但他平时跑步。哎，有人问今天的课是在哪里耶？OK，我们 monitor 一下有没有人失踪。我先开始。OK。嗯，where did you find us? Where did you go just now? There's a notice on the board, right? Made on the whiteboard. Oh, you didn't go in. Okay. Have you submitted? Yes. Okay. Okay. Uh, okay, let's start. So let's recall the definition of continuity. So what does it mean by a function be continuous? We say that f is continuous at a point if what? At x. We use two sequences to study this continuity. What are the two sequences we look at? Right? Huh? If what? There are two sequences we look at. One sequence live in the domain. the other sequence live in the codomain. Okay. So what two sequence we are checking here? So there's a point here, right? We call X in the, so the R here we refer to the domain part. Okay. If for every sequence Sn that converges to X, then what? We can build another sequence, which is f of Sn. So what happened to this f of Sn here? Should converge or not? Should it converge? Converge to where? Need to converge to fx. Okay. So you already see that from last lecture, right? This continuity doesn't mean like the primary or high school or your calculus continuity. It's like you cannot draw. You can draw a graph of function, continuous function, without lifting your pen. Why? Remember the last time we create this weird function here, which is continuous at every irrational point. Okay, but discontinuous at every rational point. So you can see that this graph, you can see some isolated point, right? You see there's one there, the top there. It's not close to the other points. Okay, but this one is continuous at irrational number. Where's the irrational number? It's in the middle of any two real numbers. And you can see those dotted line. Sorry. Actually, the continuous at every irrational point. Where's the irrational point? What's the value? F value of irrational point? Other 0. Okay. We define fx to be 0 when x is irrational. Okay, so they are like line here. Okay. But there are also infinitely many points that is not 0 here. Okay, especially when these points are the rational. Okay. So you need to like irrational is 0, and then somehow at the beside you is one rational, then you come out with it. And then beside rational, maybe it's another irrational, you go down. Then rational you go up. Irrational come down, rational go up. Okay. Yeah. So please learn the proof of how to show that f is continuous and discontinuous. Okay, so how to show a function is continuous at one point? Huh? How to show? From the definition just now. Recall. What's the definition? If you want to show f is continuous at x, what do you need to show? For every sequence xn that converges to x, you need to show that fsn also converges to x. But if we want to show that it's discontinuous, negation of the statement is what? Negation of the statement is what? For every become there exists some sequence that converge to x, but fsn doesn't converge to fx. Okay. Okay, so maybe we can think more closely what this convergence means. Let me see. So look at this picture here. Okay. So suppose we have these continuous function. Okay, seems very continuous, right? Okay. So we look at one point here. Look at this particular point here. Okay, let's call it. Okay, this point is P. Okay, so I want to show that this graph here continuous at P. Is it continuous at P or not? From your point of view, any definition you use, whether this is continuous, you can use the left limit, right limit, and then converge, and then it attains the point there. Okay, it's continuous. But how to see from our sequence definition here? How to see from our sequence definition here? Suppose we build, so if it's continuous there, right? No matter how you take the sequence of Sn converging to P, Fsn have to converge to Fp. Okay, so let's say we pick one particular one. So what sequence we pick here? So we pick sequence like this. So what sequence is this? Okay, so we start from the endpoint here and then go all the way to P and then exit P and then return to P and then exit a little bit and then I go back to P again and then like this. This is my sequence. Does it make sense? Can you guys understand this picture here? Okay, so my sequence is going from one endpoint to the other endpoint, pass by P a bit, and then coming back, pass by P a bit, and then going the other way again. So that this sequence is converged to P. Does it make sense? Okay, so now we want to look at what is Fsn here. So what is the F of every point here? Okay, can we imagine what happened to F of every point here? So this F of every point here really given by this function, right? Okay, so if I start from the right endpoint here, the F here is all the way at the top here. Okay, so I can plot out the graph of, for example, let's call this S1, right? So here is S1, S2, S3, S4, and so on, right? So I can plot out what is FS1, FS2, FS3, and so on. Okay, so you can see that when my sequence in the domain go from the right to left, my F values go top to down, and then to top again, to down again, and then trying to actually really also converge to some point here. What's this point converge to? Yes, this is exactly the FP. Okay, so you see this line here also matching the FP here. Okay or not? Okay, so you can see that if you have a sequence in the domain, you also have a convergent sequence at the codomain. Make sense? Make sense to you? Okay, so let's see. I give you another example, discontinuous one. Let's see what happens when we play the same trick here. So you see, this function, is it continuous or not? Where's the continuity point here? This is similar to what we have seen last time, right? The fx equal to x and then fx equal to x minus half. That piecewise function there. So this is not continuous at the, let's say we call this point P again. Okay. So we play the same trick. We use the same sequence here. Okay, they converge to P. But what happened to f of the sequence, f of Sn? You can see that the f of Sn also split into two divergent sequence. Does it make sense? Does it make sense why it looks like this? So for example, if I pick this point here, right? So let's say I pick the right inside this point. So all the points here follow this graph here, right? So it's going down. Okay, but once you pass P, right, what happened? You go to the top again. And then slowly going down once you reach the left end point. So you're going up and then you're going down again. And then when you coming back, what happened? You see the graph increase again. Okay, so you increase again. But once you pass by P, what happened? It's like a dripping stock. Suddenly jump to 0. Okay, so once you pass by P, you jump to 0 again. And then slowly you increase here and then coming back. Right? Increase and then coming back. Okay, so you got an increase, right? Increase and then coming back here. And then If you pass by P to the left-hand side, again, increase, right? And then if you turning back, so, okay. So once you reach to the left-hand side of P, you increase to a point, and then you start decreasing. Okay, once you go, going to the, so you're turning back from the left-hand side, what do you get? When you go close to P, it get increase again. Okay. So, does it make sense? So you increase, so you suddenly from P, so let's say this point is FP, right? And then you go to the top. So once you pass FP, so you straight away jump to the top point here, and then you go decrease again. Then you return to FP. Does it make sense? No. Anyone following? Okay, so you can see that f of this Sn, right, is not converging. There's no limit point here. Okay, so this is a visualizing way to see the Sn to P and the Fsn to P. Okay, so far any question or not? So can you recognize the continuity and discontinuity through sequence or not? Okay. A question? Don't be shy, just ask. Just think of it, there's only you and me in this classroom, no others. Okay. So far, okay? Also good. All right. So let's continue. So we will explore some property of continuous function. We explore some. So suppose fg are functions on a domain A, which is continuous at a point P. Then what can we do? Okay. So in the sequence case, right, we look at convergent sequence, two convergent sequence, and then we can add them up. We can multiply them. What can we do? We can scalar multiply it. Okay, we can divide it also. So in this case, it's the same. Okay, we can add up functions, continuous function, but still continuous. Hello. How did you manage to find us? How did you manage to find us? Oh, you just hear the voice. Okay, good. Yeah, next time we use voice. Okay, and what else? I can multiply by a scalar multiple. Okay, by C. It's still continuous. Okay. What else? I can take product of them. It's continuous. And I can take portion of them, or I divide. It's still continuous. But there's a point here. This G applied on P shouldn't be 0, right? You cannot divide by something 0. So how do we define f plus g? If f is a function, g is a function, how f plus g is a function? How f plus g is a function here? How do we define s plus g as a function? So to, sorry? You want to try? Yeah, so if you want to define f plus g as a function, so you need to tell me if I input an x in my domain, what do I get from this function here? What should I get? What should I? Fx, I just simply take fx plus gx, right? Because I know what happened if I apply x to f. If I know what happened if I apply g to x, I just add the value up. So this is what we call a pointwise addition. Pointwise. Okay. This is what we call a pointwise. So similarly, CF is what? I can just take f applied to x is a real number, and then I multiply by c, another real number. Okay. Fgx on x is just fx times gx. F divided by g is what? Fx divided by gx. So that's why we want to require that gp is not 0, because if I evaluate x function at p, if I divide by something 0, then this function is not defined. Okay, so how to prove this? Any idea not? How to prove this? Alright. Yeah, what do we want to show? Let's say we want to show the first one. F plus g is continuous at p. What does it mean? Every sequence that converges to p, I want to have f plus g of that sequence also converge to fp. Okay, so let's write down the statement first. So let's quickly write down the statement. So suppose Sn converge to p, want to show that f plus g of xn also converge to p, right? But like what I said just now, how do we define f plus g on Sn? How do we define this? This is defined by what? Remember that this Sn also live in the domain of f and g, right? The domain of f and g. So what? Yeah. Oh, sorry, I missed out. So it should be f plus g p. Okay, thank you. Okay, so what is f plus g on Sn? How do we define it just now? Fsn plus fgn. Sorry, gxn. Right. How about f plus gp? Fp plus gp. So this question becomes what? The conversion become the conversion of Fsn and GSN. But what do you know about Fsn and GSN? What do you know about F and G? Yeah, continuous. So every Sn converge to P, you know that Fsn will converge to Fp. You know that GSN will converge to GP. So if you want to talk about the addition of two convergent subsequence, what should you use? What should you use? You have two convergent subsequence, convergent sequence here. Okay, let me write down. Since F, G are continuous, we know what? Fsn converge to Fp and GSN converge to GP. Okay, so you know that these two converges. Can you show that the sum of the two convergent sequence converge or not? What do you use? You use sequence limits law, right? If An converge to L, if Bn converge to M, An plus Bn converge to L plus N. Okay? Fsn converge to Fp, GSN converge to GP. So Fsn plus GSN converge to Fp plus GP. So really the same. So you see, so the continuity here really boils down to the convergence of sequences. Okay, because this is our definition of continuity. We define continuity based on sequence. Okay, so you can go back and do exercise, prove all this. Okay, actually you can do the proof using sequence of limits. Okay, so the other will left as exercise. Left as exercise. So you use the limit law of convergence sequence. Okay, so we use the limit law of convergent. Okay, no? Okay. So you can prove it using limit law of convergence. So you see, we can multiply, we can add, we can scalar multiply, we can do product, we can do quotient. So what does it mean here? So we can say, we can build a corollary that every polynomial function is actually continuous. Okay, so this is a fact that we achieve. So next time you see polynomial function, it will be continuous. Why? Why is it true? Why is it true? Corollary meaning follows from the previous result. So why does it follow? You start from what? So how does polynomial function looks like? What are polynomial function? What are polynomial function? Polynomial. What are the monomial? What are called the monomial? What are monomial? So should I define this? Let's define it then. So a monomial is the term x to the power I for some I in z. Okay, so these are the monomial. Okay. So what are the polynomial? So these are the monomial. So what are the polynomial? In x, so let's call it P. So let's say this monomial in x then. So what's about polynomial in x? Is Px equals to let's say a0 plus a1 x2 x1 plus a2 x2 plus a3 x3 plus dot up to an xn for some n in n, and then where should we consider our polynomial at? We can take AIs to be in real or OI. Right. What are the examples of polynomial here? What are examples here? What are examples? Px equals to what? To what? Px equal to 1. Sorry. Plus. What do you say, Loha? 1. Sure. So you can take Px equal to 1 plus x squared. Okay. So the result here is to say that every polynomial function is continuous. Why? Sorry? Why? Because how do we build all these number up? How do we build all these polynomial up? It's like a product of x, right? And then add up with different x. Yes, some are monomials. So how do you build our monomials? what is Px equal to x? So namely the identity function from R to R, which is sending x to x, is continuous. So how do you build other monomial from identity function? You can take product of identity function. Okay. And then scalar multiple of identity function. And then you can, how to build the scalar term? You can really divide by identity function, because identity function at where? Yeah, okay, depends. Okay, depends. I mean, if you don't want to build a scalar function, actually you should show that also the scalar functions, or really the constant function. Okay, so the constant function, let's call it let's say call it what? Fp, such that you send everything to P is continuous also. Okay, so we have established that scalar function, I mean constant function, is continuous, and then identity function is also continuous. Then using scalar function and identity function, you can build all the polynomials. Does it make sense? You believe me or not? Seems like don't believe me. Okay, so for example, just now we write Px x at 1 plus x squared, right? So how to build this our map like this? Okay, so really you see 1 as a function of x, and then x to be the identity function, right? Identity function on x. How should I write this? So okay, I should write this. So I should write like identity x, and then plus identity x times identity x. And then, yeah. So really what I'm doing, so I'm seeing 1 as a constant function, and then identity as an identity function, identity squared applied on x. So this is my polynomial. Does it make sense? So you see, I don't just see 1x squared as number or variable. I see them as a function. Okay, I see them as a function. Okay, I see them as a function here. This 1 here is not number 1. Is the function that send everything in the domain to 1. Does it make sense? Okay. Okay. Any question up to here? So this is very important phenomenon to see when we want to go to prove more general or result. Okay. Does it make sense? Okay. All right. So next, we will establish another theorem. So which is I'm not sure you been using this result all over the time, which is the compositions of continuous function is. So the composition of continuous function is continuous. So what does this mean? So it means that if f is continuous at P and G is continuous at Fp, what do we get? Then Gf, okay, the composite function Gf defined by what? How do we define this as a function here? So you need to tell me, if I fit x to this G composed with x, what happened? How should we define this? Yes, so we apply f on x first, and then fx become a number, so I can apply G. Of course, fx the domain So of course, the range of f need to be the domain of G so that I can, so this thing makes sense. Okay, if you send x outside, then G have no control, then you do nothing to this point here. Okay, so you need to make sense of the domain first. So what happened to this function here? So this composite function is continuous. Why so? Why so? Yeah, why? Very quick proof. So suppose Sn converge to P. Okay. Want to show what? F on G on Sn also converge to F on G on P. But what is F on G on Sn? This is defined by, hey, sorry, I think I mixed the direction. Oh, miss some of the direction here. Okay, so let's say what is a G on F on Sn? So it is just F applied on Xn and then G applied on Xn. GFSN. Okay, and then what's the goal here? It becomes G of FP. Okay, but by assumption, we know what F is continuous. What do we get if F is continuous? Where is at F continuous? Continuous at P. So I have a sequence Sn converge to P. F is continuous. So F. So F Sn will converge to FP. But what? But we also know that G continues at where? Where does G continuous at? G continuous at FP. Okay, so G is continuous at FP. Meaning what? I have a sequence that converges to FP. G is continuous at FP, meaning what? G of Fn's converge to G of FP. But what are these two values here? These are just composite function apply on Sn and apply on P. Okay, so it's very straightforward. Once you write down your goal, these things become very straightforward. So since G is continuous at FP as Fsn is a convergent sequence converging to FP. So we get that G of Fsn converge to G of FP. But what are these? These are just by definition of G of F on Sn and G composed with F on P. Okay, so this is what we want. Okay, easy to follow. Okay, so far so good. So from now on, what can you use? You can use that every polynomial is continuous. So, and you can use that every composition of continuous function are continuous. So what else continuous function you know? So another continuous function is not included in polynomial yet. So we will see that. So should we put as a theorem or what? Just put as an example first. So the square root function is continuous also. Okay, the square root function is continuous. On what set here? So where does square root function define? On the interval from 0 to infinity, including 0. Okay. Should we do this in class or not? Sorry? Do you want to do together or do it together? Okay. So let's prove that this is continuous at the interval from 0 to infinity. Okay. So how do we show this? So meaning you need to take any x in this interval, okay, if xn converge to x, want to show that square root function. So how do we write down this square root function? What do I mean by square root function here? So this f here is defined from 0 to infinity to really, what do you get from this number here? Also from 0 to infinity, right? Okay, but how we define this square root function? So x going to square root x. Okay, so this is what we mean by square root function here. So if we have xn converge to x, we want to show that square root xn also converges to square root x. Oh, does it make sense? This is our function here. This is what our function do. Right, so what to do here? Any idea? So you can get some help from your previous knowledge. So what do I mean by that? Try and plot this graph out if you can. Whenever you can, try and plot the graph out. Okay, because plotting graph not need technique. It's just get a domain and then get the image, and then you plot it out. So something like this. Okay. So I think let's break into two cases. Okay, let's break into two cases. So later I will tell you why we break into two cases. Let's see the x equals to 0 and x greater than 0. Okay. So let's see why I break into two cases here. So you see, if I want to go to 0, right? How can I go to 0? My sequence really can only go from the right to left. Okay. But if my x is a little bit away from 1, okay? So let's say we zoom in a bit. Okay, zoom in a bit. So let's say this is the x here. Okay, how many ways to go from this, go to this point here? There are a few ways, right? You can go all the way from the right to that point, or you can go from the left to that point, or you can do what we did just now, like alternating around this point here. Okay, so this will kind of affect our analysis on this point, the limit on this point. Okay, so let's say we split into these two cases, whether it works or not. So let's try. So let's say case 1. Okay, x equals. Okay, so if xn want to converge to suppose Sn converge to 0, what does this mean? What does this mean? Go back to sequence. So what does it mean by convergence of the sequence? For every epsilon greater than 0, there exists a what? Natural number depend on epsilon such that for all the terms n greater or equals to n epsilon, we have what? Absolute value of ASN is less than epsilon. Okay, but where can you pick this Sn from in this case here? So this Sn is absolute value, right? So where can you pick the Sn from in this case? Your Sn really only live in the interval from 0 to infinity. So this Sn here is always positive. Okay, so really this is just Sn itself. Okay, so this is just Xn itself. What more? What's more? What's more? What's more? What's more? You know more. You can lower bound this Sn here. Lower bound by what? Yes, 0. Okay, the least number you can go is just 0. Okay, so you really get this inequality here. 0 less than equal to xn less than equal to epsilon. Okay. So remember, what's the goal you want to prove here? What's the goal you want to prove here? What's the goal you want to prove here? Remember our goal. Our goal is what? So let's write down our goal. We want to show that square root Sn converge to square root x. In this case here is what? Square root x. In this case here is square root 0, which is 0. Okay. So meaning what? Meaning for every epsilon greater than 0, there exists, let's say this is another epsilon. Let's call it epsilon square root. Okay. In n, such that for all n greater or equals to this n epsilon square root here, what happened? Square root Sn is less than epsilon. Okay. Can we do it or not? Can we do it or not? Can we do it or not? How? Huh? Square what? So if you square both sides, right? So this is true. So we know that square root Sn is also positive in our case here. And we can really square both sides. So what does it mean here? What does it mean here? So we can, so it's like this. So now we need to fix epsilon greater than 0. Okay, because our goal is to show for all epsilon, right? So we need to fix an epsilon greater than 0. Then there exists an n, okay, depend on epsilon squared, such that if n greater or equal to n epsilon, we have what? Xn is less than epsilon squared. But this implies what? This implies that square root Sn also less than epsilon. Okay, so this is what we want. Okay, we reach our goal here. Reach our goal here. Yeah, no. Any question? No question? So this square root Sn less than every epsilon implies what? Implies that square root Sn converge to 0. Alright? Okay. And then this is what we want to show. Square root Sn converge to 0. No question? Question? Please ask. I cannot always cater for your needs, so you need to tell me your needs. Then we can. Yes. Sorry? Oh, yeah, thank you. So, small n greater or equal to capital N squared. Yeah, thank you. Okay, so this n of e epsilon to the capital epsilon square is the n square root epsilon we need. Okay, this is the n square root epsilon we need. Okay, so this is the n. So we need to define this to be our n epsilon square root. Yes, this is the n square root epsilon that we need to choose. Okay, make sense? Okay. All right. Right. So what's next? How about case 2? What's the another reason we split out case 2 here? Okay. So let's quickly go to our goal. Let's put this as our goal 2. Goal 2. What's our goal 2? If my x is greater than 0, then this square root xn converge to square root x becomes something non-trivial. Okay, it's not 0 anymore. Okay, but what do we want to show? We want to show that this square root xn minus square root x is less than epsilon. Okay, so we want this to hold. Okay, if we want this to hold, what should we do? What can we do here? Okay, somehow we need to get control with this Sn. Okay, using what we know. What do we know? So what do we know here? By assumption, what assumption do we have here? We start with sequence that converge to x. Okay, somehow we need to use Sn minus x to control square root Sn minus square root x. How to create this Sn minus x out? Yeah, you can try conjugation, right? Okay, so let's try conjugation. What happens if you multiply with their conjugation? So you get Sn minus x over square root xn plus square root x. Okay, you can try conjugation. Then you see this Sn minus s pops up. Now what's the bottom here? Square root x is a fixed point. Right? Square root x is a fixed point. How about this one? This one is changing it. This one is keep changing it. Okay, so can we bound them or not? How? Wait, let me think. So Sn is converging, so Sn is bounded. Yes, true. That's true. That's true. But we can do a even not say stronger bound. It's a larger bound. We can simply throw away the square root Sn. Square root Sn is always positive. Yes, larger or equal to 0. Right? Larger or equal to 0. Because maybe I can sometimes reach 0 and then come back again. Go to 0. I can do the random stuff. But this square root Sn here live in the interval of 0 to infinity. So in particular, it is greater or equal to 0. Okay. So if I make the denominator smaller by removing square root Sn, right, I can make the term, I can make the quotient larger, right? So I can do this. I can do this here. Yeah, let me. S. What's the reason here? This is S square root x and it's greater than 0. Okay, no. Okay, because imagine if I add more stuff here, more positive stuff here, this quotient will become smaller. 2 over 3 versus 2 over 5 versus 2 over 6. Which one is smaller? Which one? Okay, so this is a trick you need to know in analysis. So this is the bound that you could get here. So meaning what? So meaning if I want this to be less than epsilon, actually I can make this one less than epsilon, then I can make the original one less than epsilon. Remember? Okay, so this is just working. This is just working. So we want to try and see what kind of epsilon we want. Make sense or not? Okay, so meaning if I move my epsilon goal here to here, it also works. Okay, because once I make this guy smaller, the last guy smaller, it automatically implies that the previous guy also smaller because the previous one is less than or equal to the last guy. Does it make sense? So analysis is like this. If you want to bound something, I don't know how to bound it. Find a bigger one that bounds it, and then I make the bigger one smaller. This is the idea. Okay, maybe I cannot control you. I control the one who can control you. This one is a bit like a Catholic. Right? Right. Because Jesus' mother can ask Jesus to do something. I don't know. I'm Catholic. believe it. So you cannot control that person. Control someone that can control that person. Hmm? Okay or not? Okay or not? Why jumps out this team? Okay or not? Okay, so if you cannot control the original guy, control someone that is greater than someone you can control. Okay, so I think this is also the trick you use in assignment 2, right? Okay, use someone bigger if you want to control it. Okay, so this means what? So this means that it boils down to the difference of Sn minus S less than square root x times epsilon. Okay, so now, is it clear already what kind of n you need to pick here? Is it clear from here what n you need to pick? Okay, so let me see here. So if e greater than 0, so suppose x greater than 0. So fix an epsilon greater than 0. Then there exists what? N of square root x epsilon in n such that Sn minus x is less than square root s epsilon. So such that if n greater or equal to this n square root x epsilon, we will get this inequality, but this inequality is good. Why? It follows that n greater or equals to n square root epsilon, square root x epsilon implies the difference that we want, which is square root xn minus square root x, is less than or equals to the difference of square root x minus x less than square root x. But what is this? This is what is less than epsilon. Okay. Make sense? Make sense or not? So why this part? So why this square root less than epsilon is true? This is using the what? Conjugation. Using the conjugate of square root x and square root x. Okay, does it make sense? Okay, so you start with your goal. So this is like if you read the book I show you, right? The beginner proof books, right? You see that they will have a working or they write proof analysis first. So they will start with this part here, the goal. Okay, try to see how we bound it, and then we make it into a proof. So yeah, make sense? Okay, so we have established that square root function is continuous, and then polynomial functions are continuous. And then we give some example of continuous function defined piecewisely. And then there are more continuous function to come later. Okay. Once we have two to define it. For example, like sine function, cos function, the trigger function are continuous. Why are they continuous? So to discuss about how they're continuous, you need to discuss what's the definition of them. Okay. So how to define cos and sine? What's the first impression you like? First time you heard about cos and sine? What ratio? Ratio of triangle? Oh, triangle. Okay. Sure. Okay. Sure. But then I think that one is quite restrictive, right? You cannot go to cos on angle larger than 90 degrees. Unless you can use periodic formula, right? You use the cos periodic formula. So talk about cos periodic formula meaning what? Actually, you define cos as a periodic function. Maybe satisfying some differential equation. Did you guys, when you guys learn differential equation, that define the sine or cos to you? Or the no, 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 no. For example, last time in calculus 2, right, we introduced e to the power x as a solution to some differential equation, right? I can differentiate it infinitely many times. But how about sine and cos? Did you guys introduce it or not? No? In ODE? Yes, sir. Define what is sine and cos, trigo function. Yes. Maybe. How about what? It's not coming from that way, but you can use sine and cos to build imaginary function. Yeah. So if you know about imaginary function, then maybe you can deduce sine and cos from there. But yeah. I mean later maybe we'll see it or we will just leave it. Quickly mention about it. But at some point in this course, we will talk about trigo function to be as a continuous function. Okay, so far any question or not? So far any question? No. If not, before we take a break, so later we'll talk about intermediate value theorems and then extreme value theorems. Okay. All right, let's take a break until 12:11.哦，你讲上次那个电话有 warranty 很。 then 要还钱。
是这个
，factory defect，
这个伤心
它是有 factory defect 的。
的做这 spin 的时候，安全都有问题。
它有 announce 啊，then
行动其实没有这样子。
怎么他会承认呢？你拿回去他就直接给你换吧。
我是知道问题，
then
他就讲有
跌
几个不是三个对吧？那个约定有点
哦，这样也挺好哎，这样好哎，
770块，
不然要还710，说
是这个 series 没有。
哦，这行很，就醒来过后开一下，哎，有一条线这样。
没关系啊，说就是我最近他就这样了。
对呀、
前几天一来，这
两条线了，恭喜夫人，恭喜夫人。
对，变皮了。可以。这点是提示要比较有效的。但是看来不需要。以下是就是就 degree why not why why 一直都差一点，就差一点。70/160看一下。还是那个。展示出展现的一个方标志，我展示的这个号就是
statistic 有补课，其实还有吗？之后还有之后没有？OK，但是我好像不一样，我想不一样，因为我们有一个课要拿来考试嘛，对 我还不知道，打算要补回去先，我感觉会来不及，因为现在已经延迟了。假设啦，我们补了课不是，然后我们提前结束了，然后我们就可以提前结束，就说来后面的几个课我们就早上啦，意思说了，你觉得呢？你们不要补礼拜一，你们没有时间哦。
礼拜五你们几点上课？6点到8点。拜五啊，我觉得拜一6日
拜五不是你们没有时间吗？
拜五没天。我拜四9点到9点到9点。
拜四，
拜四。
早八到晚班，你比打工人还多。
拜一拜三呢？
对了，没有啦，我们没有天天拜一啦。
那几啊？就拜一。哎，就下个拜一。上个拜一每个拜二
啊？
拜二拜三。
我想放在考试过后的那个拜一。
拜一。
考试过了拜一。考试过后的拜一有一个拜一过，我看一下。啊？
不是6点上课吗？6点上课。
考试完的拜一还有一个拜一，27号，这个想要补掉这个，这个应该拿来考试。21拿来考试，因为我本来是想补20拿来考试，但是你看你们拜一的 attendance 不好，什么你拜一也有考试啊？那我们就不要了，我们就是21考试哦。然后我是打算说把这个考试补在27，我们可以上课。耶、你要，那你23你来我的 General Topology 考试对吗？你有没有时间是能几时上课？是1点到1点，有课吗？你来我们一起考试哦，时间反正也是2周，1点到1点，星期四。OK 啊，你来我跟你讲那个班上的底下，然后你过来一起考课。所以我是想27号补掉21，当时是这样打算的，OK 吗？
不用拜。
你都没有时间，你自己都问你的同学啊，又不是
1点到6点。
啊，1点到几点
6点。
？1点到6点。
1点上课。
他们呢
？6点上课。
他们呢？
6点上课。
哦，你们也是6点上课，拜五哈？你们想要拜五啊？星期啊？变小辛苦。没有，我们打算27号补掉21的考试，不得补都可以。他们现在要决定是拜一还是拜五。拜一就这个时间，拜五就1点到6点之间。啊，拜一挺好的，因为汉维不喜欢。
换一个
很贱。没事，有3号、17号给你放。有8号给你放。
那你这个不强制的课程。
不强制，27号不强制。啊，补的那个不强制。啊，可能都不记录。哦，这样长啊？没有啦，至少一个人来我就来，没有人来那我们就不好说。OK 吗？27号，这个不强制。
更晚一点的
啊？11 to 1。现在是11点到1点，对。
有没有晚一点？
因为我也是要补一个 General Topology 哦。
让他们放前面。
但是就是他们，哎，我想一下，他们有问题吗？ 我问一下，之前好像我是记到他们有人有问题不能够上，好像有人有上课，我问一下，我再问一下，看他们是这样子，如果可以我就上了。OK，confirm，再跟你们。哦，绿色哈，本来是一些 assignment 日期来的。拜五哦，这个拜五啊，你们那什么？这个拜五，拜四还是拜五？拜四咯，拜四，呀，拜四。忘记了，我有点 mix，因为 general topology 是拜五，拜五也可以的，都可以。I mean，你们不要故意 drag 我就可以了。你要会几时考试啊？这个 week 6嘛，对不对？week 7嘛，还有 week 8，所以我们只剩下一个礼拜、2个礼拜这样了考试。OK，I will disclose the exam content soon. Then maybe this week at end of 最后一天见你们之后。And then yeah, assignment please look ahead If you got problem, quickly ask me and then start thinking about it. Okay, don't leave until last day. Sure, you cannot finish one. Okay, my assignment is not for you to do within 1 hour, 2 hours. That one is not assignment today. That one is exercise only. Okay, so let's start. Okay, so we will discuss two theorems that's very, 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 very super important in analysis. So first of all is this intermediate value theorem. Okay, so what does it mean by intermediate value theorem here? What's the statement of intermediate value theorem? So let's talk about statement and then we try and see how we think about this statement here. So suppose f is a continuous function. Of course, we like to study continuous function. Okay, you can see that there's a lot of property that hold by this continuous function here. So this continuous function is continuous on a bounded interval. So what does this mean here? So I define continuous continuity at a point, but here says that continuous on a closed bounded interval. What does it mean? I define continuity at a point, right? But here says continuous at a closed bounded interval. What does it mean? What does it mean? Huh? I only define continuity at a point, right? So what does it mean to be continuous at a closed bounded interval? It is continuous at every point in this closed interval. So meaning A also closed, B also closed, any point between A and B, it also continuous. Okay. And one more property here. If FA is less than Q and Q is less than FB, so what does this mean here? So if I can apply F to A, I can apply F to B, and there's some number between it. Okay, there's some number between these two range here. What happened? Then I can achieve this number using my function. Then there exists an x in AB such that fx equals to, I can achieve this point using my function. Okay, so let's draw some graph. So let's draw some graph here. Yeah. So let's say I have a FB here. I have a FA here. Okay. And this A and B is where somewhere around here, let's say. Okay, I have FA and FB here. And I have any point Q here. Okay, so there's a point Q here. It says that It says that's what? This point here must be achieved by some x in the middle of A and B. Why? It says if f is continuous. I'll try and think about this. Try and think about this. Try and think about this. If f is not continuous, is this true or not? I can define some function like this continuous function like this. Then my function wouldn't pass by Q. But it says that if f is continuous, your f must pass by Q1. You need to somehow connect A and B together. You somehow need to connect AFA and AFB together if your function is continuous. Right? Correct or not? So if you want to connect these 2 points together, somehow you must pass through all the middle point. Okay? Let's say I'm very funny. Right? I don't want to pass through it. Okay, I don't want to pass through. I don't want to pass through. I never pass through one. But I still want to go here. How? You must pass through it. Okay, you must pass through this point here. Okay? But for a general function, right, you may pass through multiple times. Okay, you may pass through multiple times. Okay, but the question is just asking about there exists one that pass through it. Fx equals to Q. Okay, does it make sense? Okay, now got a better idea on this intermediate value theorem. Okay, so these conditions are very important. Continuity, okay, so that you want to pass through. Closed bounded interval, also very important. Okay, later we'll see how important is this. Okay, and then you can achieve any point in between FA and FB. Does it make sense? Yeah. Okay. So far, got any question? No? All right. Okay, good. So let's see how we prove this. Okay, so there are a few ways to do this. I think we will at least do 2 ways. All right, let's do the first proof here. So let's do the first proof. Okay, how to think about achieving this Q? Existence. Okay, existence. How should we think about this? Okay, we should use some bounded above property here. There are a lot of boundedness, right? Closed bounded interval. Okay, and then the images of f is somehow bounded also. Right? Okay, so first proof. Okay, so it's the first proof. So we will construct. So you see, this is a typical analysis proof. We will construct something that's useful. Okay, let's see how useful is this set here. So we construct this set, set of A. What is this set here? This set is everything in the domain, okay, bounded by A and B, and all the value that is less than or equals to Q. Okay, can you see what we are trying to do here? This is a bounded above set, right? Okay, and this is non-empty. Why is this non-empty here? Why is it not empty? What do we know about FA here? FA is less than Q. Okay, so it satisfies this property here. A is the endpoint of the interval. So then A is non-empty since FA. So since A is in A as FA is less than Q by assumption. So this one is by assumption. And bounded above or not? Bounded above by what? No way. You want to bound who? Q is to bound the value of X. But this set here is the point from A to B. Yes, it's bounded above by B. So this is a non-empty bounded above set of real number, subset of real number. So by completeness axiom, sup A exists. Okay, sup A exists. Sup A exists. And what? And we will prove that f of sup A is what? Is what? Put is equal to Q. Okay, this is the point that we want. But is it clear that sup A is inside the closed interval AB or not? Is it clear? Why sup A is in the closed interval AB? Is it clear why? It's bounded above by B, right? So the largest sup A you can get is just B. Does it make sense or not? Okay, so first, sup A is in the interval of AB. Okay, because sup A must be less than equal to B. Okay, because it's the least upper bound, and it must be less than every other upper bound, in particular B. Okay, and if it is less than B, then what is the definition of a closed interval here? All the number that is greater or equal to A and less than equal to B. Okay, so the smallest it can get is what? Smallest it can get is just beta A. And then the largest it can get is only B. Okay, so it's some number inside there. We can find this number because of the completeness of real number. Okay, this number exists. I don't know what number is this, but this number exists. Make sense? Okay, no? Yeah. All right. So now next thing. Okay, so we know that this point is in this interval. Next thing to do is to show that f of this is really the Q we want. Okay, f of x is really the Q we want. So how do we do this? How do we do this? So we need to involve continuity here. Okay, so how do we involve continuity here? Yeah. So what do we do? So what do we do? Try and think about how can we prove f sub A equals to Q. Sorry? Sub A equals to Y. FB is what? FB is not Q. FB is something greater than Q. Right? Remember? FB is just something greater than Q. Okay. So how should we argue that Or should we argue that f sub A is Q? Hmm? Hmm. Yeah. Sure. So what AN you want to pick here? Any idea? Try and think how to prove this. Maybe Larry idea is one of the good idea so that you can use continuity of F. Okay, let's try. Let's try and construct this guy here. So let's construct this yn here. So we construct yn to be the minimum of B or sub A plus 1 over n. Okay, so what does this do? So imagine what is happening now here. So remember, once I give you a closed interval, please pull out your real line. Okay, and then we are considering some sub A happening somewhere in the middle here. Okay, and what am I doing here? This yn. This yn is considering either B or something a bit to the right of sub A. So what does this mean here? So what does this mean here? So for each n, okay, what do we have? We have yn is greater than x because on the right hand side, right? And more importantly, yn is not in A anymore. Why? Because sub A is the largest thing that satisfies the A property. Okay. So in this case here, if you are not in A means what? If you are not in A, meaning f of yn is greater than Q. Okay, so you know that f of so then f of yn is greater than Q. Okay, but we know what? But this yn here should converge to x. Right? This is by construction. You can see that. Sorry, what is x? It's a sub A. Converge to sub A. Right? Because it's sub n plus 1 over n. Okay. So this implies what? F of yn really converge to f of sub A. Okay. So what can we do here? Can we do here? Let me do here. Is it enough to say that this is equal to Q or not? Hmm. If you have a sequence which is always greater than Q, if it converges, right? Where should it converge? It should converge to sup A, but what does this sup A satisfy? Sup A is really less than equals to B, right? Sorry, B or Q? Q. F, oh sorry, sup A is less than or equal to B, sure. F of sup A is less than or equal to Q. Okay. But you are something that's always greater than Q. Can you converge to something less than Q? Hmm? If it converges to something less than or equal to Q, it should really converge to Q. It cannot converge to something strictly less than Q. You get what I mean? You get what I mean? Because if you want to converge to something less than Q, your term should at least go to Q, and then you go to something less than Q. But your term is always greater than Q. Okay, so it cannot converge to something less than Q. If it converges to something less than Q, meaning you need to be very close to something less than Q. But to be close to something less than Q, it should at least pass the Q point. Okay, so if it converge to something less than or equal to Q, it must be equals to Q. Or we can put a lemma here. Okay? So let me put down the therefore fx equals to Q. Okay. Otherwise, we can make a lemma here. So put a lemma here. So what's this lemma here? If yn greater than Q for all n in n, and yn converge to L, where L is less than equals to Q, then L should be equal to Q. Okay, so this is the lemma if you want to prove. Okay, if yn is strictly greater than Q for all n in Q and n in n, and then yn converges to something less than equal to Q, then L must be Q. Okay, it cannot be something less than Q. I will write down this lemma, but you can try and work it out also. Okay, so this is one of the proof. Okay, so this is one of the proof. So actually, this proof boils down to this lemma here. Second proof is quite similar to what we used last time. Okay, so let's prove it second way. Let's see it from a second way. So I purposely do different proof here because I want you to see how we get this intermediate value numbers in different way. Okay, so let's get this intermediate values from different way. So how to get from this way then? We will construct again. So analysis proof, right, is very always constructed. Okay, and the first time I see analysis proof, right, I will feel loss of direction. Okay, it's not like algebraic proof. If it's algebraic proof, right, like abstract algebra, how to prove? Assume definition of group and then check group, or assume the group property and then what do you guys learn already now? Huh? What else? What terms you guys learn, for example? Okay, so far permutation and then what else? So what else? Any special terms you guys learn? Terminology. Huh? What? Special? Special linear group. Permutation. What else? Huh? Huh? Louder. Orbit? Orbit of a group action? Orbit? What? What kind of orbit? Huh? Why like only two of you learn group theory? Where the others? Coset, already learn coset? Quotient group already learn? Oh, normal group, learn or not? Normal, not yet. Conjugate, not yet. Not yet. Yeah, so in algebraic proof, right, typically you just put down the definition and then the definition will tells you how to prove it, what you need to find. But for example, in analysis, right, what do we have? Every non-empty subset, bounded above subset is what? Has a supremum. So you need to go and find the non-empty subset first. Only that you will get the supremum. So analysis is kind of constructive. You need to construct. There's not one construction that works. Maybe few of them will work. Okay, so maybe at least for me, the first time I see analysis is like, why? Why you pick this? Why you pick that? It's just that it works. Okay, you can do other things as well. Okay, so let's see how this works here. So let's construct a sequence of nested interval. Okay, so this is really similar to what we have for the Bolzano-Weierstrass proof. So how does nested interval be? So I want the length to be reducing. Okay, so I take 2 to the minus. So maybe write in this way is better, of b minus a, such that what? Such that f of the left endpoint is always less than or equal to q, and f of the right endpoint is greater than q. Can you see what am I trying to do here or not? Can you see what am I trying to do here or not? What am I trying to do here? So you got these A and B and here. So A and B here, right? Okay. You have some point like F B, maybe F A here, right? Okay, F A and F B. And you're trying to reduce, okay, the interval here, say A N and B. Okay, such that what? Sorry? The length of A N and B N is getting smaller and smaller. So let's say this is my Q here. Okay. So I want to make this interval smaller and smaller and smaller around this point here. Okay or not? So let's say if you have a multiple Q, you make multiple Q. So you just make this nested interval around one of them. Okay. Okay. How about like this? If I do like this, how? This one can or not? Can I make my nested interval here or not? But doesn't make sense or in my definition. I want FAN less than equal to Q, but here is greater or equal to Q. Right. But the point is, if you make this point, right, definitely you can find some point looks like that. You can always do that, this special. You know why? If you have this point going up and going down here, but in the end, you need to go back here again. Yeah. Oh yeah. I think that's the special case. Is it a special case for this one? Is it called a Rolle's theorem? That one. Yeah. So if you are okay, you are saying that if 1 point is less than 0, 1 point is greater than 0, then you must pass through 0, right? Yeah. It's the same. It's the same, but that one is the center at 0. But can you see what is going on here? What happened in this proof here? If this case happen, right? Oh, you are like, oh my god, how am I going to make this nested interval? But the point is, you will definitely have another point that looks like that. Lower at the left, higher at the right of P. Does it make sense? This is the special of this proof here. Okay or not? Okay. Okay. So we can construct this nested interval around Q. Okay. So how do we do this? So as follows. So how do we make this? So first, obviously, we pick the largest one as our first A1. Okay. We pick A and B with A1, B1. And then next, what do we do? If f of an plus bn over 2 is less than q, what am I doing here? What is an plus bn over 2? A plus b over 2 is the midpoint of AB. If this point is less than equal to q, then I just let this point to be my an plus 1, correct or not? Because this point is the point that is on the left and then less than equal to p. And I just keep my bn plus 1, right? The previous b is already having fb greater than q. I just keep it. And if not, what happened? If in the case that the midpoint here give me some point that is greater than q, what do? Then I just keep the left endpoint and then change my right endpoint to the new midpoint. Okay. So for example, in my case here, okay, you see, in my case here. So let's say I fix middle point, or middle here. So middle somewhere around here, right? You see, middle here is some point is greater or equals to q. Okay. Then what? Then I pick this guy as my q, as my bn, and then I keep the smallest guy as my fa. Okay or not? Okay. Okay. Yeah. All right. So next, so from here, what do? So you can see that this interval, right, is become smaller and smaller and smaller. Okay. So in particular, the sequence of an and bn converges. Okay. So it converges to a unique point x. So this is what we proved last time. So if you have a nested interval which converges, it converges to some point in the interval, okay, of an, bn for every n. Okay. So we want to prove that this fx is actually q. We want to show that this fx is actually q. So if you manage to make this nested interval, and then we want to show that it is really doing what we want here. Okay, so it is really covering this point here. Okay, so how should we do this? Okay, we still haven't used continuity yet here, right? So how do we use this? So what do we have here? What do we have? Let's see what we have. We have FAN is less than equal to Q all the time. Okay. We also have FBN greater than Q all the time. Okay. And then we know that FAN converge to FX. Sorry. We know that, so we shouldn't put like this. So we know that since AN converge to X, BN also converge to X, then by continuity of F, what do we know? FAN also converge to Fx, and then FBN also converge to X. Okay, and then FAN is always less than or equal to X. Okay, so FAN is always less than or equal to Q. Okay, so meaning what? Fx here is always, I will finish it. Sorry, yeah, soon. Okay, so FAN is always less than or equal to Q, right? Okay, meaning what's happened to the limit here? It is also less than or equal to Q. Okay. How about FBN here? If it is always greater than Q, the limit should be greater or equal to Q. Could be equal, right? It's like 1 over n. You are greater or equal to 0. Okay. So in one case, you have to converge to something less than or equal to Q. In one case, you have to converge to something greater or equal to Q. So in both cases, to hold, it must converge to Q. There cannot be something strictly less than Q, or cannot be strictly greater than Q. Okay, otherwise these two limits got a gap. Okay, they must equal. Okay, no. So if you like, you can prove a lemma again. Okay, lemma again. If FAN less than or equal to Q, and it converges, that limit must be less than or equal to Q. And if FBN greater than Q, the limit must be greater or equal to Q. You can prove this lemma. Okay, if you like. I can write down the lemma also in my book. Okay, so in this two cases here, if you want both of them to be true, they must be equal to Q. Okay. Yeah, so a bit tricky in both cases, we prove that Fx is equal to Q. So basically, we are using the property of limits. Okay, so that's why we spend a lot of time talking about convergence of a sequence. Okay, so it really boils down to this convergence of sequence. So if you like to be very pedantic, right? So we will put here, okay, here as a lemma 1 and lemma 2. Okay, but for both of them to hold, they have to be equal to Q. Yeah. So if there's any gaps here, it should be here. Okay, this 2 point here. Why? When you have terms, every term less than or equal to Q, if it converges, it must converge to something less than or equal to Q. If it is greater than Q, why it must converge to something greater or equal to Q. Okay, no? Make sense? Okay. Most probably you can prove by contradiction here. If it converts to something less than Q, you might have trouble already because every term here is greater than Q. You can find some epsilon gap. If If all your term is less than or equal to Q, it converges to something greater than Q. Again, you have epsilon gap between Q and that limit here. If your term is bounded below by Q, how you go above Q? So how you say you converge to something greater than Q? Does it make sense? Okay, so you can show these two lemma by contradiction actually. Okay. All right, any question before I take a break? If not, see you tomorrow with Snake. Okay, I'll bring Snake. And this is quite sleepy actually. Okay.